Going on to number 6 and 7 on the final fall 2020. So this one is evaluate the line integral f dot dr, where f is given by this xyi, so f of xyz is xyi plus 4zj plus 3yk. And the curve C, this, is defined by the intersection of this plane and this cylinder. So here's the cylinder, and I drew this without a coordinate system because you really don't need one. So here's the cylinder. So it's a right circular cylinder like this, okay? And then this plane isn't necessarily represented by what I have, but it essentially cuts it through on a diagonal. So you don't have to actually draw that exactly, but you could. It's y is arbitrary, so it comes out on the y-axis, but essentially this is what's going to happen. It's going to come through and cut this thing on this diagonal. So that curve that you get by the intersection of the cylinder and the plane is that. So that's your curve C. So to actually integrate around that would be kind of difficult. You essentially would be needing to find the intersection of these two curves. So there's another way of doing it, and that's where I tell you to use Stokes' theorem. So if you project this region down into the xy plane, then you get the region D, which would be this set of points. So this is your region D right here. Now, then what you do is you can write x plus z equal to 5 in terms of a level surface. So I'm going to define g of x, y, z and set it equal to 0, essentially. So you don't have to say that, but essentially this is set equal to 0. So we have g of x, y, z as a level surface. So the level surface is this. Okay, and it goes on forever, of course. It's a plane. Okay, so then what you end up doing to apply Stokes' theorem is you apply the theorem. So you apply the theorem. So you all of these values, functions need to be continuous first partials. Everything else the theorem says. So make sure you look up the hypothesis of the theorem for Stokes. So state hypothesis is true, and then you can show that the closed curve C of f dot dr, or you can use the theorem, is equal to the double integral over d of the curl of f dot ds. And so that's the ds, again, is one of those labels that you can't really evaluate. So you need to convert that into something we can evaluate. So what you do is you say that this is equal to the integral over d of the curl of f dot in ds. So that's something more we can evaluate. And then the next step is the evaluation theorem, which we would derive. It's in my notes somewhere, but so it's that over double integral over d. So you're integrating over this region d right here. Okay, I don't want to mess that up. Okay, so that region, I meant to do this. So this is your region d right here, and it's the projection of basically the intersection down into that plane. So then you have that's equal to the curl of f dot, and then you do the gradient of g dA. So the gradient of g, if you recall, so here's defining my g. The gradient gives you this normal vector in. And so, and that's derived with this notation, well, in the book or my notes or whatever. So a lot of stuff there that we didn't have a chance to cover directly, but you can do these calculations pretty straightforward. So what I would do next really is just do the curl of f. And so you want to show all these steps when you do the curl. So you get negative I minus xk, which is -1, 0, negative x. Okay, so make sure you are showing those steps. Where I put in the dots, you need to have work to dot, dot, dot. Okay, you'll get that. Then you also need to do the gradient of g. That's pretty easy. The gradient of g. So here's your g. It's just those partials. So that's pretty straightforward. That's just partial of g with respect to x gives you -1. Respect to y gives you 0. And with respect to z gives you 1. And then from there, you can take those and do their dot product. So we can say that this is, we'll move it down. So this star is equal to the double integral over d, and then you're doing this dot product. So this step you can show maybe. And it's dot -1, 0, 1 dA. And so you do the dot product, and now you're going to end up with a double integral over d. And this just becomes then 1 minus x dA. And you can see that pretty straightforward there. It's this times this, which is 1, plus 0, plus the negative x. So it's just 1 minus x. So to do this, you probably want to change to a different coordinate system because you're integrating around a circle. So probably change to polar. Well, I guess technically, no, it would be polar in this case, huh? Not cylindrical. Because it's a double integral, so you just change the polar at that stage. Okay, so you should be able to evaluate that. So put in some steps here, show some work, and you have your double integral 0 to 3, and you're going all the way around, so 0 to 2 pi of r minus r squared cosine theta dr d theta. So r dr d theta. So it'll be, probably should have shown that step. So you end up with 1 minus r cosine theta. Sorry, I figured I'd just write it out directly. So it's 1 minus r cosine theta. And then r dr d theta. Okay, then you can work it out from there, of course, etc. And then it becomes pretty straightforward. So you're taking something that would have been really difficult to integrate over that curve, and you're using Stokes' theorem to apply this. So look up the hypothesis, and it has to do with continuous first partials. I think this is a simple closed curve, things like that. So state hypothesis. And then fill in these details here, 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 whatever else you want to do. Okay, next one, 7, is divergence theorem, which I tell you here. All right, so we didn't talk about flux directly in a problem session or anything, but this has to do with flux. So it's like you got to picture a like a field going through a surface like that. Okay, so a field's going through the surface. That's your vector field. That's F. So it's going through that. Okay, so divergence theorem basically, so the divergence of F is basically adding up the partials. So look up divergence. So you do the divergence of F, ends up being partial of F with respect to X, and then you're adding them up. Partial F respect to Y, partial F with respect to Z. So this is a scalar function. Once you do the divergence, you go from a vector function to a scalar function. So then the flux, which is the double integral over the surface, so it's a surface integral, is F dot in ds. So it's calculating basically how the F is acting on the surface. That can be turned into a triple integral. So this calculation is often easier. Triple integral over the solid Q of the divergence of F dot dv. And so that formula becomes really nice because this is a scalar function of x, y, z, and then it's just dv. So you're doing a triple over this. Well, for what's given for a sphere of radius r, that triple can become spherical coordinates, which is nice. So do the divergence of F. Okay, so calculate that, and you should get 12x squared z, right? So that's just doing each of these partials basically. So that's 12x squared z, 12y squared z, and 12z cubed. Just FYI, you can factor out the 12z, which might help simplify it. To factor out 12z, and then you end up with x squared plus y squared plus z squared. But in spherical, what is x squared plus y squared plus z squared? So if you change the spherical, you can't read that. I forgot I'm using a different color on a white background. So that's rho squared. So rho squared is the sum of the squares of those components, so which makes it nice. So change the spherical on this one, and so you get that this equals. So let me put this down here. So change to spherical. I mean, you're only going over a sphere, like why not? Okay. And so you get the triple integral of 12 and then z in spherical. So look up spherical. And so z is rho cosine phi. So you have you can define, or it's derived what x, y, and z are. So z is rho cosine phi. So you now can substitute for these, and then don't forget your integrating factor, which is rho squared sine phi. So that's going to go in here as well, and then d rho d phi d theta. So you get 12, and then you'll get rho cosine phi, and then you'll get rho squared, because that's x squared plus y squared plus z squared. And then you get rho squared sine phi d rho d phi d theta. And then what are we evaluating for rho? Rho goes from 0 to r. Right, so it's 0 to r. And then phi goes from, it's the whole thing, right? So it's just, this is just a sphere. So that goes from 0 down to pi. So you're doing one sweep to pi. So that's your, sorry. I always hate when it messes up like that. That goes 0 to pi for your phi, which is next. And then all the way around, 0 to 2 pi. Okay, so you have all of that. Of course, work all that out, and it should work out nicely in the end. Okay, I won't tell you what it is, but it works out really nicely. So, but the rest of it, I mean, it really is just polynomial or just cosine to simplify. So again, that's taking where you have to calculate flux over a surface integral. And instead of doing this with your n, you would have to get your n and all that, which to find n, you'd have to define the surface and then calculate that. So often doing the divergence of your vector field makes it much simpler, and it simplifies it. Not all the time, like if you have other weird trig functions or something, but for a polynomial like this, making it, well, the components are polynomials, then it makes it into a nicer form. All right, so make sure you show, well, this is pretty straightforward, not much to show there really, but then do your calculation and see what you get, draw your pictures. Oh, and what I forget, I almost forgot hypothesis. Make sure you look up and state hypothesis. Make sure the hypothesis is satisfied for all this stuff. It's a closed surface, that kind of stuff. Continuous first partials, that your S is closed surface, that sort of stuff. So make sure you look all that up. Okay, and then that's it. So spend some time writing it up, doing a little studying as you go, and that'll be it. So here's everything. If you have any questions, let me know.